the big thing we're studying this week is that idea of a linear relationship. And so this is going to be bivariate data, the bi and bivariate meaning two, so we have two things going on. And one example I'll give you is the relationship that ice cream has with the number of murders that are had in a city. So let's say New York City had 100 million ice creams sold. I don't really know if that's exactly the right number. And then they had 300 murders in the city that year. We'd put a dot right here to represent that data point, because for the 100 ice creams that were sold, it matches up with the 300 murders. And then if we kept doing that for other cities, I don't know, maybe Baltimore somewhere down here. What's another big city? Cincinnati, LA, something like this. Eventually you'll get a scatter plot of data points. And the funny thing is, with ice cream sales and with murder, the scatter plot usually makes a linear trend like this. We call it a linear trend because it goes up in a straight line. It follows some sort of straight line pattern. Okay, you could have linear trends that are downward trends too. Up isn't necessarily the only way. This is a linear trend, but it's just a negative linear trend because it's going down. That's the main idea of what we're trying to study. We're trying to analyze these linear trends and see if they really are, if these two variables of ice cream sales and murder are really related to each other, or maybe they're not significant enough. Maybe they aren't a close enough line to say that they are related to each other. And so if you look at this graph, the more ice cream that's being sold, the more murders are occurring. So it kind of sounds like if you sell more ice cream in your city, the more people are going to get killed, or vice versa. Maybe the less people that die, the less ice creams that are sold. So we can talk about that in the discussion board, why that is. It's obviously not ice cream is causing people to get killed, but we can talk about why that is on the discussion board. But that's the main idea of a linear relationship. It's plotting data points on a scatter plot or a scattergram, and then when you see that straight line happening, you would say a linear relationship exists between the two variables. So we call the variable on the x-axis the explanatory variable. That's one thing you'll want to keep in mind, is that the x-axis always has the explanatory variable on it. So this time, the number of ice creams being sold was the explanatory variable. And we would say that because the original hypothesis that I was making was that ice cream was causing people to get killed. Any variable that's causing an effect in another variable would be called the explanatory variable. So that makes everything on the y-axis a different label. We call that the response variable. The response variable is being impacted by the explanatory variable. So keep that in mind as you study. X is the explanatory, y is the response variable. So researchers want to show, with a reasonably low level of doubt, that this is a linear relationship. If they can give us some sort of number that tells us that this is really, really close to a straight line, we can test out that number, and then we can either say yes or no based on random variance, random noise going on. So the way we test that out is by calculating a correlation coefficient usually. A correlation coefficient is a number that's it's either bigger than -1 or it's less than +1. And if the correlation coefficient equals exactly 1, so actually I should back up here. R is this correlation coefficient. It's something we can calculate with StatCrunch or any other type of statistical software. So it can be calculated by hand. It takes a little while because you need a formula, you need to go through each data point. But again, this is just a number that we calculate based on this scatter plot or this scattergram. You put your data into StatCrunch, you tell it to calculate your correlation coefficient, and it will spit it out for you. And then we can analyze that number. If that R that you get out is exactly 1, that means your data isn't just looking like a straight line. It is a straight line. It lands perfectly on a linear trend. If your R is a -1, the same thing, except this is a linear trend going this way. Your data points, oops, that's not on the line. Your data points would land exactly on the line. And if you have an R somewhere in between, an R of 0.5, that means, well, it's kind of a weaker trend. Dots are spread out, but you can see that as the x-axis increases, the y-axis increases. And then just like when we said there was a negative r, if you have an r of negative 0.5, that's still saying it's a weak trend. It's just decreasing as you go along the x-axis. So that might be an r of negative 0.5. So again, something you should check out the discussion board for. I'll tell you how to do this in StatCrunch. But r tells you the correlation. You calculate r to find the correlation coefficient. That tells you how scattered your data points are. And so every time we're trying to analyze a scatter plot, I keep drawing a line to show the linear trend, the straight line. We use stats softwares to tell us exactly what this line is, an equation for the line. And you might recall way back in Algebra 1, one of the first things I tried to teach you was y equals mx plus b, which is the general form for a straight line. We're going to use statistical software to come up with the least squares regression line. And it will tell us what the slope is of our line. It'll tell us the y-intercept. Okay. If you get a negative slope, then you have a negative trend like this. If that was a positive, and that's supposed to be a 7, my handwriting is terrible, but if that was a positive 7, it would be some sort of positive sloping trend. The least squares regression line, it tells us the equation of the line that best fits the data. What your computer does is it calculates the distances apart all the data points are, and it finds out the line that minimizes all these distances I'm drawing in blue here. It minimizes those distances so you have a line that perfectly cuts through all the data. Okay, so that's a third key idea you'll be studying, is how to find the least squares regression line that matches your data. One little tidbit that might help you out down the road here. One thing that's always guaranteed, because the least squares regression line always perfectly balances out the data, you're guaranteed that the mean of your x data, which is the mean of your explanatory variable, and the mean of your y data will always be a data point somewhere in there, because the mean is the mathematical center. So if you have the mathematical center of this x line and the mathematical center of the y line, it has to land on your least squares regression line somewhere. Try to keep that in mind. So those are the big ideas that you'll be studying this week. There'll be some finer points, as there always is, but you can always use the textbook feature on your homework questions to jump right to the part of the textbook that you need to study. You can always use the Ask My Instructor button. Ask My Instructor button to send the question directly to me, and I'll be happy to answer. But I just wanted to give you a heads up on the key ideas for this section, so you can know what to expect.